Hello students, I am your lecturer Shanta Mukartihal. I welcome you all for the today's session on Unit 1 ARM Embedded System and ARM Processor Fundamentals. The topics which I have covered in session 3, that the previous session, are von Neumann architecture and hardware architecture and ARM architecture families, ARM data flow model. So in the previous session, we discussed what is von Neumann architecture and hardware architecture. I'll just revise the topic in few minutes. In von Neumann architecture, the program and data both can share the same memory. There is a common memory for program as well as a data. But in hardware architecture, there is separate memory for program and separate memory for a data. So this thing we studied with the help of diagram. And next we studied about the ARM architecture families. So there are three architecture families, ARM families: ARM 7, ARM 9, and ARM 10. So ARM 7, ARM 7, under ARM 7, we will be going to study ARM 7 TDMI in the later chapters. So those things we studied in the ARM architecture family. ARM 7 has pipelining, and under pipelining we studied three stages: fetch stage, decode, and execution. ARM 9 is a 5-stage pipelining architecture method. So in ARM 9 we have 5 stages. They are fetch, decode, execute, memory, and write back. They are the five stages in that pipelining. The last one is ARM 10. It is 6-stage pipelining. So the 6 stages are fetch, issue, decode, execute, memory, write back. So these are the different architecture families we studied in the ARM architecture families. Then later we discussed about ARM data flow model. So with the diagram I explained how many elements or how many blocks the data flow model has. So total it has 8 elements, and each element is responsible for certain function. So the 8 elements, just I'll recall the 8 elements. The first element is instruction decoder, which is used to decode the instruction. Next is sign extend, which is used to extend the sign of the number. And third one is register file, which is used to save the data in the register file. It acts as a memory. Next, there is ALU for doing arithmetic and logical operation. And next there is barrel shifter. With the help of barrel shifter, we are going to pre-process one of the operand and then give it to the ALU. Then MAC unit for multiplication, and then address register to hold the address, and the last element is incrementer to update the address which is present in the address register. So these things we studied in the previous session. Let us begin our session with today's topic. That the topics which I am going to cover are 3-stage pipeline ARM 7, advantages of pipeline, disadvantages of pipeline, and registers. So what is 3-stage pipeline in the ARM 7? There are 3 stages: fetching the instruction, decoding the instruction, and executing the instruction. If you write a program with the help of the instruction, you cannot execute directly. First, you have to fetch the instruction from the memory. After fetching, the instruction should be decoded. After decoding, it will be ready for execution. So it has to pass all 3 stages: fetch, decode, and execute. So what is fetch? So fetch, it loads an instruction from the memory. Decode, the instruction with what is the purpose of the instruction, that is identified by the decoder section. It decodes the instruction. The last stage is execution stage. It processes the instruction and writes the result back to the register. In three-stage pipeline, the pipeline is a mechanism. It is used by the RISC processor to execute the instructions. Pipeline increases the speed of the execution by fetching the next instruction while other instructions are being decoded and executed. So what is pipelining? The process of fetching the next instruction while the other instruction is executed and decoded. So this process is called as a pipelining process. So the three stages in the pipeline just now we studied: fetch, decode and execute. You can see here in cycle 1, the first instruction is fetched. What is the first instruction? Here I have shown add instruction. So in the first cycle, add instruction, first instruction is add instruction, that is fetched, and no instruction is decoded and no instruction is executed, because in the cycle 1 only one instruction can be fetched. When we go to the second cycle, so in the second clock cycle, the first instruction what we fetched, it is decoded here, and the second instruction is fetched. So sub is a second instruction, subtraction instruction. Sub instruction is fetched. At the same time, in the clock cycle 2 only, the first instruction, that is add instruction, is decoded. And execution, nothing is execution because no instruction has come to this level now. In the third clock cycle, the third new instruction is fetched, that is compare, CMP. And second instruction what we already fetched, it goes to the decoding stage. And the first instruction, it is under a decoding stage. Decoding is completed in the second cycle and it goes to the execution stage. So you check the cycle here. Cycle 1, only first instruction is fetched. Cycle 2, second instruction is fetched, first instruction is decoded. Cycle 3, third instruction is fetched, second instruction is decoded, and third instruction is, second instruction is decoded and the first instruction is executed. So this is called as pipelining. So here the fetching, decoding and execution, their work is simultaneously going on in the clock 3, that is cycle 3. So you can check here the 3 cycles again I have shown: fetch, decode and execute. So to fill this, where it is filled, see the previous diagram. The pipeline, this is called as pipeline. The pipeline is filled in the clock 3 cycle. Cycle 3, the pipeline is filled. So fetch is filled, decode is filled and execute is also filled in third clock cycle. So the time it takes for instruction to fill the pipeline is called as a latency. So latency is the time period. So how much time it takes to fill the pipeline? Check the diagram here. In cycle 3, the pipeline is filled. In cycle 2, pipeline is not filled. Cycle 1, pipeline is not filled. Cycle 3, pipeline is filled. So how much time it has taken to fill the pipeline? Cycle 1, cycle 2. In cycle 3, the pipeline is filled. The time taken to fill this pipeline is called as latency. So it is shown here. Latency, time it takes for the instruction or filling the pipeline, is called as a latency. Then where we'll get the output? So see the second cycle here: fetch, decode and execute. So execution comes only in the third cycle. So we get the output in the third cycle, so that is called as throughput. So see the previous diagram. So in first third cycle, the third instruction is fetched. In third cycle, second instruction is under decoding process, and in the same cycle the first instruction is executed. Here I will get the output. So this is called as throughput. So at any time slot, 3 different instructions may occupy. So now onwards, from cycle 3 onwards, at any point of time, 3 processes will be continuously going on. So you see the again previous diagram. In the fourth cycle, again new instruction is fetched. Compare instruction goes to the decoding state. Subtraction instruction goes to the execution stage. From third cycle onwards, we start getting the output, throughput from the third cycle onwards. So for every cycle, we start getting the output. So at any time slot, 3 different instructions may occupy each of these stages when the processor is executing data processing instructions. So for these data processing instructions, the latency period is 3 cycle. What is latency? The time required to fill the pipeline. So how much time is required? 3 clock cycles are required. So the latency is 3 clock cycles. This is for only data processing instructions, not for other instructions. So for data processing instructions, the latency is 3 cycle. And what is throughput? After third cycle, we start getting 1 instruction execution per cycle. So every third cycle onwards, for every cycle, we get the throughput, that is 1 instruction per cycle only. You see this sequential instruction processing. So let us study if pipelining is not there. If pipelining is not there, what happens? We'll check in this diagram. So sequential instruction processing, then pipeline instruction processing. Both the diagrams we'll study now. So this is fetch stage, decode stage, and execution stage. So the 1, 2, 3, 4, 5 up to 15, they are marked as clock cycles. So they are called as cycle 1, cycle 2, cycle 3, cycle 4 up to cycle 15. What happens in cycle 1? In the sequential means one after the other. So in sequential, assume the instruction A is fetched. The instruction here marked as A, B, C, D and E. How many instructions I have shown here? 5 instructions. So in first clock cycle, instruction A is fetched. In the second clock cycle, so since this is not a pipelining, the same instruction has to be decoded. And in third clock cycle, the same instruction A is executed. So one after the other instruction execution takes place in the sequential instruction processing. So A fetched here, decoded here, and execution. After the execution over, in the fourth clock cycle, the second instruction is fetched. So the second instruction is fetched in fourth clock cycle, that is instruction B. In the fifth clock cycle, the same instruction B is decoded, and in the sixth clock cycle, it is executed. So after the sixth clock cycle, the execution of the second instruction is over. And third instruction C, it is fetched in the seventh clock cycle, because 3 cycles are required for instruction A, 3 cycles are required for instruction B. Now in 7th cycle only we can fetch the third instruction C. And in 8th cycle, the C is decoded. And in 9th cycle, C is executed. In the same way, the next instruction D is fetched in 10, decoded in 11th cycle, and executed in 12th cycle. And the fifth instruction E is fetched in 13th cycle, decoded in 14th cycle, and executed in 15th cycle. So every instruction requires 3 cycles for the execution in a sequential instruction processing. The sequential instruction processing at 1 step per clock cycle, only 1 step happens, either fetch or decode or execution. Simultaneous operation will not happen like in a pipelining process. So how many cycles are needed then? So that can be calculated with the help of this formula. How many instructions I have shown here? 5 instructions. Each instruction require how many clock cycles? 3. So the total number of cycles required is 5 into 3. Number of instruction into number of stages, that is 5 into 3 is equal to 15 cycles. To execute 5 instructions, we need 15 clock cycles. So let us study the same 5 instruction, how it is executed in 3-stage pipelining process. So let us begin our pipelining process now. In cycle 1, instruction A is fetched. We know that pipelining, we can fetch, decode, that we have studied already. In the second cycle, instruction B is fetched, instruction A is decoded. simultaneous operation is possible in pipelining. In third cycle, instruction C is fetched, instruction B is decoded, and instruction A is executed. In the same way, the instruction A needs 3 cycles to get the to give the result. So after third cycle, A will be executed and the result will be ready. In the fourth clock cycle, instruction D is fetched, and see what we have fetched in the previous cycle. It is decoded and instruction B is executed. In the fifth cycle, instruction E is fetched, instruction D is decoded, and instruction C is executed. And in the sixth cycle, if I don't take any instruction for the fetching, so this will be vacant, and instruction E, which is already fetched, it goes to the decoding stage, and the instruction D, which we have decoded, it comes for the execution stage. In the seventh cycle, if we don't fetch anything, because we have only 5 instructions already we have fetched, so this will be vacant, and decode, there is no instruction for decoding here, but already instruction D is decoded, it comes for the execution stage. So total, to execute the fifth instruction, the 7 cycles are required. See the previous diagram. So to execute the fifth instruction, it comes in the 15th clock cycle for the execution. But in pipeline stage, in 7 cycle only the fifth instruction gets executed. So how many clock cycles are required? The formula is number of instructions plus stages minus 1. Stages, what are the stages? Fetch, decode, and execution. 3 stages are there. 3 stage minus 1 if I take, it becomes 2. Number of instructions are how much? 5. 5 into 5 plus, sorry, this is plus 5 plus 2, 7 cycles. So total 7 cycles are required to execute 5 number of instructions. See, just the same instruction, if we go for sequential, it is requiring 15 cycles, but if I come for pipelining, it takes 7 cycles. So the pipelining in theory, so by doing this pipelining method, the performance is increased and over unpipelining core by a factor of number of stages. See here, it is 7 here, there it is 15. How many times it is increased? 7 into 2, 14. So by number of stages it is increased, the performance is increased. So here you can check the table. In this table I have given for 5 instruction, the clock cycles required in sequential is 15 and the clock cycle needed is 7. Use the formula number of instruction plus stage minus 1, we get 7. And the increased performance, by how much factor the performance is increased? 7 divided by 15 divided by 7 you do it, so we get 2.14. Another example we'll take, if there are 10 instructions, how many cycles are required in sequential? 10 into 3, 30. How many cycles are required in pipeline? So that is 10, this formula you apply, 10 plus 3 minus 1. 3 minus 1 is 2. So 10 plus 2 is 12. So we require 12. So what is the increased performance? 30 divided by 12. So it is 2.5. In this way, the remaining 2 you calculate, you will get 2.88 and 2.94 increased performance factor. So now you came to know that if I use 3-stage pipelining process, the throughput increases and the performance also increases. So the ARM architecture, ARM7 architecture, it uses 3-stage pipelining process. So 3-stage ARM pipelining with an example, ARM7 processor has 3-stage pipelining architecture, fetch, decode, and execute. ARM9 has 5-stage pipelining architecture. ARM10 has 6-stage pipelining architecture. So what are the advantages of this pipeline? So by seeing those two the figures, sequential and pipelining figures, you can yourself write the advantages of a pipeline. So the first one is it increases the throughput. The number of instructions per second increase will be more. So number of cycles required are less. Because of this, the throughput increases. And how it is expressed? Million instruction per second. Always the throughput is given in terms of MIPS, million instruction per second. And the second advantage is it increases in the number of pipeline stage, increases the number of instructions executed simultaneously. So as you increase the number of stages, the number of instructions executed also increases. The pipeline CPU works because it is doing all these functions simultaneously. Definitely CPU must work at higher clock frequency. So pipeline CPUs work at higher clock frequency than RAM clock frequency. Then more pipeline stages will result in greater throughput. If the stages are more, definitely the throughput will be greater. Then pipeline increases the overall performance. So as the result we get earlier, as the throughput we get greater, definitely the overall performance of the CPU increases. So these are the advantages of pipeline. Very important. You need to remember all the advantages for your exam. So then what are the disadvantages of pipeline? So sequential is easy to design, but in the same cycle, execution, decoding and fetching simultaneously doing it is a complex task. So design of pipeline processor, it is complex and it is also expensive. Instruction latency increases in pipelined processor. So what is latency? To fill the pipeline, initially for the first instruction to come out for the execution, it needs the number of stages. If it is 3 stage, and after third stage, the first instruction is executed. In cycle 3, all the stages will be filled. The process of filling the pipeline is called as latency. So this latency increases if the instruction latency increases in pipeline processors. The throughput of pipeline processor is difficult to predict. Sometimes if all the instructions are having the equal uniform size, then definitely one after the other cycle it will be executed. So some instructions require some machine cycle for the execution. If some other instruction require some other machine cycle, then it is difficult to predict the pipeline processor, because if all the instructions are having the same size, then this process continues. If they are not having the same size, definitely it becomes difficult to predict the output. There are branch delays when serial instructions are executed concurrently. So if there is a branch instruction, so after decoding, first the branch instruction is fetched, then it is decoded. After decoding, it will come to know that it has to jump to some other location. Then it becomes difficult in the pipelining process. So there are branch delays when serial instructions are executed concurrently. When a program branches, entire pipeline must be flushed or cleared, because if it is a branch, it has to go to that place, and from that place what are the instructions are there, they are executed. So during that time the pipeline must be cleared, so in order to fill the new instruction. So whenever the program branches, the entire pipeline must be cleared. This will become the drawback or the disadvantage. Throughput decreases when the code contains many branches. So like this, if the code has many number of branch instruction, every time it is decoded and branches to some places and execute those instructions, come back. So by doing this, the throughput increases. So it is good for non-branching instructions. So if there are a branch instruction, definitely the throughput decreases. If each instruction in pipeline is not executed before the next instruction, it causes program to behave incorrectly. So suppose the branch instruction arise, definitely it goes to some other location, then the program will behave incorrectly because the pipeline will not be filled, and again it has to be flushed or cleared. So this situation is called as a hazard. So whenever the branch instruction comes for the execution, then the pipeline hazard occurs because it has to jump to some other location. Then the pipeline has to be cleared. So all this is called as a pipeline hazard. These are the important disadvantages of pipeline. So remember, the processor is complex and expensive, and latency increases, and we cannot predict if the branch instruction occurs, and the pipeline must be cleared if the branch instruction arises or comes into the pipeline, and the pipeline hazard occurs. So these are the disadvantages of pipeline. Next topic is registers. What are the different registers we have in the ARM processor? So you can see the diagram. Look at this diagram. Registers. Under that, there are data registers and processor status register. It is classified into two types: data registers and processor status registers. Data registers, they are marked from R0 to R15. Total how many data registers? 16. Starting from R0 to R15, 16 registers. And how many processor registers? CPSR and SPSR. CPSR stands for current program status register, and SPSR stands for saved program status register. And the data registers are classified again as general purpose registers and special purpose registers. General purpose registers are from R0 to R12. Special purpose registers are from R13 to R15. R13 is called stack pointer. R14 is LR, it is link register. R15 is program counter, it is PC. So this is the classification of registers. So this register, many registers are active and some are hidden here. So what are those active registers? Let us study now. The active registers in user mode and a system mode. I'll discuss what is user mode and system mode in the next session. So the active registers are from R0, R1, R2, R3, R10, R13. So they are from R0 to R12. They are called as a data registers. And special registers R13, R14, R15. They are special function registers. Why they are called special function? Because R13 is meant for stack pointer, R14 is meant for link register, R15 is meant for a program counter. So these three are special function registers. Remaining from R0 to R12 are data registers. And there are two more registers, status registers. So they are CPSR, current program status register, and SPSR is there, but it is not visible in the diagram. So it is shown as a dashed line. So there are two processor registers, CPSR and SPSR. CPSR is visible to the user. SPSR is hidden here. So it is not shown in the diagram. So total, there are 18 active registers. So you can count the register here. R0 to R15, how many registers? Total 16. And CPSR 17, SPSR 18. There are 18 active registers including 16 data registers R0 to R15 and 2 processor registers CPSR and SPSR. Among 18, one is hidden. SPSR is hidden. CPSR it is visible to the user. SPSR is not visible to the user. All registers starting from R0 to all register, they are all 32-bit in size. And data registers, there are 16 data registers R0 to R15. They are visible to the programmer. And general purpose registers are R0 to R12. They hold either data or address. So data registers are R0 to R15. General purpose register R0 to R12. So why you can ask me, R0 to R15 are there. Why the general purpose registers are taken from R0 to R12? Because R13 onwards, it has got the special function. R13 stack pointer, R14 link register, R15 program counter, So they cannot be used as a general purpose register. So R0 to R12 can be used as general purpose registers. Special function registers. So the three special function registers are there, R13 to R15. So the first special function register is stack pointer, that is register R13. It is used as a stack pointer. So what is the use of stack pointer? Stack pointer always holds the address of the stack top. So on the stack, the top location, the address, it will be there in a stack pointer. So this pointer is available in stack pointer is available in a current processor mode. I'll tell you what are these modes in the next session. Link register, it is R14 register. It is called as a link register. So the core puts the return address in the link register whenever it calls a subroutine. Whenever the main program calls the subroutine, so the execution of the current, after completion of the execution of the current instruction, the control has to transfer to the subroutine. Subroutine is a small program. So after going into the subroutine, again it has to come back to the main program. So while coming back, the address of the instruction will be stored in the register R14. So the content of the R14 it will take, and it will come to know where it has to come back to the main program. Then program counter is register 15. It is used as a program counter. It contains the address of the next instruction to be fetched. The address of the next instruction to be fetched is available in PC, and link register holds the return address from the subroutine. So from the subroutine, if you want to come back to the main program, the return address is stored in a R14, and stack pointer always holds the address of the stack top. The program status registers, there are two program status register, current program status register, saved program status register. So current program status register, so what is its function and what are the bits, what is the bit structure of CPSR, that we'll see it in the next session. So this saved program status register, it is not visible in user and a system mode. So we studied the different registers available. What are the different registers available in ARM? And we studied the pipelining, three-stage pipelining, and what are the advantages of pipelining over the sequential instruction processing, and what is latency, what is a pipeline hazard, what is throughput. All these things we studied. Based on that, now we'll solve some multiple choice question. The first question is, what are the pipeline stages in ARM7? So I told that ARM7 is a three-stage pipeline structure, ARM9 is 5-stage, and ARM10 is 6-stage. So you find out what are the three stages. The first option is fetch, write, decode. So option A is wrong because the right option is not there in ARM7. Second option is fetch, decode, execute. Yes, this is a right answer, because we fetch the instruction, we decode the instruction in second cycle, and we execute the instruction in the third cycle. So the option B is a right answer. So check the option C. So it has execute and write. So this is also not there in a ARM7. It will be there in ARM9 and a ARM10. So the right option is option B. So while studying the registers, I explained which register can be used as a general purpose register and which register can be used as a special function register. Special function register, stack pointer, program counter, and link register. So here it is given R0 to R15, the general purpose register, or R13 to R15, R0 to R12, or option D is all. See here, R0 to R15, it includes both general purpose registers as well as a special function register. So the option A is wrong. Option B is R13 to R15 is given. It is special function register group. So option B is wrong. Option C, R0 to R12 can be used as a general purpose register which holds either data or a address. So option C is a right answer. Next question is, Which one of the following is not an advantage of pipeline? You should remember what are the advantages. Then only you can answer this question. Increases the throughput. Yes, by pipelining method, the throughput is increased. Design of pipeline processor is complex and expensive. So whenever we get a word expensive, complex, definitely it will be not the advantage. It will be a drawback only. So the option B might be there. The answer, you can check it later. Then pipeline CPU work at higher clock frequency than RAM clock frequency. So because it is doing all the functions simultaneously, it work at a higher clock frequency, and more pipeline stages result in a greater throughput. So more number of stages, more throughput. So this will be the advantage, and this is an advantage, option C. Option A is an advantage. Then right answer is option B. Here the question, read it properly. Which one of the following is not an advantage, they have asked. So option B is a right answer. Identify whether the following statements are true or false. So R13, so before answering this question, you read the statements correctly, then you check the options. The first option is R13. It is used as a stack pointer and stores the head of the stack in the current processor mode. R13, R14 and R15. R13 is for stack pointer. What is the function of stack pointer? It holds the address of the stack point. So statement 1 is correct. R14, it is used for as link register. So what is the use of link register? Whenever we use a subroutine, the control transfers from main program to subroutine. To come back from subroutine to main program, we need to save the address. That saved address is available in link register. So R14 is a link register where the core puts the return address on executing a subroutine. So this option 2 is also right. Statement 2 is right. Statement 3, R15 is what? Program counter. So program counter always holds the address of the next instruction to be fetched. So statement 3 is also right. Now you check the options. All the statements are true. Option B, 1 and 2 are true. Option C, 2 and 3 are true. Option D, 1 and 3 are true. So since all the options are true, the right option is A. Option A is the correct answer. So which of the following statements are true with respect to pipelining? Again, the 3 statements are given. Read it carefully. Pipelining is an implementation technique whereby multiple instructions are overlapped in a execution. So it is implementation where multiple instructions are overlapped. So when in the third cycle, third instruction is fetched and second instruction is decoded and first instruction is executed, but it is not visible to the programmer. So the programmer cannot see these actions, what's happening inside. Each step is called pipeline stage or a pipe segment. Then pipeline machine cycle is the time required to move an instruction one step down the pipeline. So this is a machine cycle, the time required to move the instruction one step down the pipeline. So after third cycle, fourth cycle onwards, it goes one step down. So the options are, all the statements are true. 1 and 3 are true. 2nd and 3 are true. None of them are true. So the answer is A. Option A is right answer. All the options are statements are true. So when the processor is executing simple data processing instructions, the pipeline enables one instruction to be completed every clock cycle. This is called as what? So after every third clock cycle onwards, after every clock cycle, we start getting the output, and that is called as a throughput, not the latency. Latency is time required to fill the pipeline. So they have not given the question like time. So we get the output for every clock cycle, they have said. So it is, the option is throughput. It's not the latency and execution. Definitely the option A is a right answer for this question. So we solved some multiple choice questions on today's session. So in the next session, I'm going to explain the different topic, the process, some processor modes you studied in this session. You did not understand that because I have to explain those topics in the next session. So let us meet in the next session. Thank you.